Hello everyone, I'm Priyanka Verma and in this video I will explain about controller area network. So this intended audience for this video is absolute beginners of CAN protocol knowledge. This presentation or this video mainly covers the frame part and how the communication happens, like the transmit and receives, state diagrams and the frame format, and in case of errors, how the errors are handled and what are the rules for counting the errors. The remaining part of the protocol will be covered in my second video. So I'll begin with the introduction here. The CAN was developed in 1983 by Bosch, and in 1986 it was officially released by SAE. This protocol allows microcontrollers and devices to communicate with each other's applications. It is a message-based protocol. For each device, the data frame is transmitted sequentially, but in such a way that for more than one device, but if in such a way that if more than one device transmits at the same time, the highest priority device continues and the others back off. It is a multi-master serial bus. It connects the ECUs, which can be better called as nodes here. It is majorly used in automotive domain, but these days it's used in medical domain as well and various other domains. It is a conventional two-wire bus. It's a twisted pair with 120 ohm resistor termination at each end. It is done to reduce noise and to ensure that reflection does not cause any communication failure. It uses differential wire AND logic, which here means here in this protocol, the dominant bit is 0 and the recessive is 1. So it can give up to 1 Mbps of speed until the bus length is of 40 meters, and after 40 meters the speed starts to decrease. Now there are 4 types of frames: data frame, remote frame, error frame and overload frame. So firstly, data frame. The data frame contains the node data for transmission. The remote frame requests the transmission of a specific identifier. For example, there's a requirement of a specific message. It tells that this particular identifier message with, the message with this particular identifier is required, or it's requested. Next comes the error frame. It's transmitted by any node detecting an error. Overload frame, it injects a delay between data or remote frame, or between two data frames or two remote frames. So next we have here is the base frame format. So firstly, there will be idle state check preceded by at least 11 recessive bits, which means 11 times 1111. And then if the bus is idle, it comes the start of frame, which is a single dominant bit. Dominant bit in this case, as I told you earlier, in case of CAN is 0. Then it comes the identifier. Now there can be two types of identifier, 11-bit and 29-bit. In case of a IDE, in case IDE bit is set to dominant, which is 0, then it is a 11-bit identifier. Else, if the IDE bit is set to 1, that is recessive, then a 29-bit identifier is there. So next comes the control after identifier. Now control is limited to the binary values, like it goes through like 4 times 0 or until 4 times 1, and basically tells like what is the, what is the DLC, what is the length of the data that's going to be transmitted. And the other two you see here are the reserved bits. Yeah, these R1 and R0 are the reserved bit in its IDE for 11-bit identifier. So the next thing I would say is the data that can be transmitted is up to 8 data bytes. And then after that comes the after transferring the data. See, firstly we saw if the bus is idle. Yeah, we found it idle. Then we sent the start of frame. Okay, that marks the beginning of the frame. And then we have the unique identifier, and it can be 11-bit or 29 bits. And then we told how long is going to be the data, and then we sent the data. After that comes the check. That's the cyclic redundancy check. In this case, it's a 15-bit, it's a polynomial, and its ending is marked with a delimiter of recessive, the recessive bit, like it's 1 in this case. With the help of this cyclic redundancy check, the chances of um, um, undetected message error probably goes less than 4.7 into 10 to the power minus 11, as low as that. And what happens in this CRC, the transmitter calculates a checksum from the transmitted bits and provides the result within the frame CRC field. It is also able to detect the burst error, like up to 15-bit. And after this error is completed comes the acknowledgement. So what happens here is a CAN is broadcast based. So for example, if I send a message, it goes to everybody. It's broadcasted to all of the nodes. So regardless of it is required to that node or not. So when each and every node receives that particular message, the node has to send an acknowledgement for the error-free error-free transfer. If the transfer was not error-free, then there will be no acknowledgement. Each and every node that received any error-free transfer must send a dominant bit, which is 0, during the acknowledgement slot, even if the message was not intended for the node. So the next is next comes the after acknowledgement comes end of frame. This marks the end of the frame. These are the 7 recessive bits, means 7 times 1 1 1 1 1 1 1. And then comes the interframe space that's injected to to give the space between two frames. This is always 3 times recessive bits, means 3 times 1 1 1. Now next here we see is recessive state diagram. So firstly, there will be a wait for idle bus. Like firstly, it will check whether the bus is idle or not. When when the bus is idle, we reach this state. It's idle. Then marks the beginning. That's the start of the frame. The start of the frame here is a dominant 0 bit. If the valid start of frame bit is there, then we will wait for the transfer of the data. If it's not the valid one, then it again goes back to the idle state and checks, and it will try to send again. In case of the valid start of frame bit, happens the transfer. After the transfer happens, like if it's a valid transfer, then it will go, the acknowledgement will happen, and then again it will go to the idle state, and then again a message can be sent if everything is good. Now if the invalid transfer is detected, an error flag is sent to the bus. And it can be either ways. There can be one more way an error flag can be sent. That is when we wait for the transfer and the transfer is detected, it's completely fine, but the acknowledgement is not received or the invalid acknowledgement is there, then again the error flag will rise and that will be sent to the bus. Now next comes the transmit state diagram. Firstly, we'll wait for initialization, and that's like the bus is idle, and this is for the transmission part. So how it happens here is, firstly for transmission we must have something to send. So application has a message to send, let's assume, and then it sends the transfer. If the transfer happens correctly and acknowledgement also happens, then it again goes back to the idle here, and then we can again send the next message. For example, while sending the message here, there can be an error while the transfer happens. In case that happens, then error flag is sent. And if there was no error in the transfer, and we were waiting for acknowledgement, either we got no response from the acknowledgement or we got an error flag response, then again error flag is raised. And while this is raised, we try to reattempt the transmission. For example, there can be an error that in first case there is no response, then try again to get the response, and it keeps on trying until the error counter reaches it's greater than or equal to 256. After this count, the bus goes in off state. It neither sends or receives anything, and it sends like we need to reset the CAN controller. So how this TEC, the transmit error count or the receiver error count in case of receiver end, how this is calculated, we will see in the upcoming slide. So here we go, error handling and counting rules. So each CAN controller implements a receive and transmit error counter, that is REC and TEC, to determine how the process detected transfer errors. The counting of these increases or decreases according to the protocol stated rules. So firstly, we'll see the receiver error count rules. So here we talk about the counter. So as a rule, firstly, the counter is initialized to 0. And then in case of if there is a error that, for example, say there is another node which does not acknowledge, then this counter is increased by 1. And if there was a successful message transmission, then it is decreased by 1. If there was an invalid transfer, then the error counter is again increased by 8. So if in case we are having repeated invalid or transfers, and even after reattempting we cannot reach the idealistic proper state of receiving a message correctly with acknowledgement and with all the checks, it again tries. And so for example, here we see when this RAC is increased by 8 again and again, and it reaches 128 count, then the error goes in passive state. Before that, when error occurs, firstly it's an active state from 0 to 128, and after 128 it goes to the passive state. Here in transmitter error count rules, we will see it further. Same here, when there is a successful transmission detected, this counter will be reduced by 1 and increased by 8 when there is a error during the transfer, and also it will be increased by 8 when it's detected that any of the nodes have sent the error flag while awaiting for the acknowledgement. It can be no acknowledgement or negative response to the acknowledgement. And this is how, as we have seen earlier, from 0 to 128 the error is active. From 128 to 256 the error goes passive, and after 256 the bus goes off and there is a signal sent to reset the CAN controller. So we discuss here only to until here for today, and we will talk about more on CAN protocol. There are several other parts which must be covered, so we'll talk about them later. And thank you very much for patiently listening to me.